Hello and welcome to another tutorial. We are going to continue on discussion of the classes and objects. We've looked at a couple of different items, and now let's see how we can actually create objects, which we said that the concept of object is that a class definition is like a blueprint. Each class definition gets compiled to a separate class file. The name of the type is not necessarily the name of the class or the class file. That's because if you're in the source file, your class definition has a package declaration, the name of the type is actually the fully qualified name, which is always relative to the class path that you define when you launch your Java application. And we said that these class path configurations are normally hidden from you by the IDE, and we said that you should always use an IDE. That's one of the best practices of Java. And then I always say that know your IDE, learn your IDE even before learning your programming language, right? The concept of IDE is that's important, right? It's very important. I cannot emphasize enough how important it is to know your IDE well enough, okay? So let's see how, basically we've already seen how to use the new operator in Java to create instances or objects of a class, but let's give it a more formal definition and understanding. So creating and using objects, understanding what objects are, and a typical Java program creates many objects, lots of objects. In fact, the whole idea of Java being based on object-oriented programming was because we wanted to create many objects. It's typically object-oriented programming is easier to model real-world applications, real-world systems. But then the problem is that a lot of objects are created as local variables, and we saw that as soon as you go out of the method call and return, all the local variables go out of the scope. And we also saw that in our discussion of the methods, that references, local variables, or in general variables that have the type reference, these are just pointers. And we said that every variable in Java has to be in the scope of a method. There is no global scope by itself. So, and every method in Java has a stack frame associated with it, right? And we said that even when you launch your Java application, it's actually the main method of a particular class that is being executed. So the first stack frame that gets generated is always the stack frame of a particular main method that you launch your application with. And if you have variables, local variables in that method that are of type references, and we said that references are just glorified or handicapped pointers, right? They don't have the complexity, or basically references in Java hide to some good extent the complexity of raw pointers that we have, for example, in C++ or C. But then once you go out of the scope of a method, if you have a local variables that are of type references, and we said the local variables are always stored on the stack of the method. But then when you use the new operator, the object itself, because when you use the new operator and call a constructor, the object gets created and it holds a initialized state. And a state of the object means there are some variables in the class definition that hold some values, and these have to be stored somewhere in the memory, right? That's the whole idea. Every variable has to be stored in memory. Local variables are stored on the stack. A stack frame is just some memory that is reserved for the method itself. And then a state of the objects are always stored on the Java heap, which is a much larger memory area than the stack frame of each method, okay? So I want you to understand the distinction between the stack frame and the local variables. So for example, if you look at this line of code, we are creating a local variable because we are in the scope of a main method. And this local variable is of reference type or pointer types, right? Point, rectangle, these are types, user-defined types. And these are glorified pointers or handicapped pointers. And we are creating a new object. Basically, the idea of new is you call a particular constructor, you pass some arguments to it, and then these are going to initialize the state of the particular object that gets created. So whenever you JVM executes this line of code, it creates a object, it allocates some memory on the Java heap, all right? That is enough to hold the state, all the variables of this particular class type, because JVM knows how much memory how much memory is needed to hold the state of a particular class definition. Obviously, different types have different require different memory, and then but the JVM is aware of that. So it allocates some memory on Java heap and then initializes that memory that holds the state of this object with these values 23 and 94, and then it creates a local variable on the stack frame of main, right, which is of type pointer, and it initializes this pointer with the memory address of that particular memory area on the heap that holds the state of this particular object. All right, so we create lots of objects, but as soon as we hit the end of the method, all these local variables go out of the scope and we can never use that. And if we lose a pointer to a particular object on the Java heap, obviously that means that object on the Java heap, we can never address it, because the whole idea of a pointer or reference is that you can chase or dereference it to get a hold of the state of this object, right? That's the whole meaning. You have some data in the form of the state of an object that's stored somewhere in the Java heap memory, and you kind of need to have a pointer or a reference to be able to chase that and get to the actual state, those data. If you lose the pointer, you lose access to that, and this is when we call this object, this data that are in the Java heap associated with this particular object is now a garbage. The concept of garbage means there is some initialized memory with some state, which the user defined it and initialized that object in the Java heap, but we lost our pointer or a reference to that memory area, and now we can never address it, so it's garbage. And then Java has garbage collector, which means frequently throughout the lifetime of the application, when it JVM runs, the garbage collector behind the scenes basically explores the memory, the Java heap, and then figures out which parts of the memory are initialized objects that are no longer referenced, and then it tries to delete them or compactify them. There are various garbage collection algorithms that JVM has, or basically various garbage collectors that come with the JVM, and at runtime you can actually configure the JVM to tell it use this particular garbage collector like G1 or 0 or epsilon garbage collector, right? And again, different garbage collectors deal in their own way with the garbage collection. So the reason that note that there is no requirement or there is no particular reason to do garbage collection or address these unaccessible object or data on the memory heap, because if you have infinite amount of memory or RAM, or maybe let's say you have your computer, your hardware has 1 terabyte of RAM, and you know that you've run your Java application a couple of times, and you know that your application probably is never going to need, let's say, 1 terabyte of memory, then you really don't need to have garbage collection, because the whole idea of memory management is that you want to guarantee that first of all your application doesn't consume a lot of memory, because obviously the application is run as a individual process by the operating system, right? And operating system is responsible for allocating memory to all processes. So if one process starts to consume a lot of memory, then that process becomes suspicious, and the operating system has to kind of deal with it, either terminate it, or I don't know, if you have an antivirus installed, maybe the antivirus flags that or quarantines that particular process. So there are some monitoring that happens behind the scenes by the operating system if an application suddenly starts behaving out of the ordinary. Okay, so garbage collector basically is in place in Java so that first of all you as a developer don't have to deal with garbage. Basically garbage means there are some objects that you've created, your application has created, and the state of that object, the data were initialized in the Java heap, but you lost the pointer or the reference to that, so that object that data is no longer reachable, and therefore it's a garbage. It has to be deleted, cleaned up, so that the memory is, so that JVM knows that that memory can be reused again, right? And there is a flag, actually there are a couple of flags that when you launch your Java application, you can tell JVM, JVM, I want you to only use this maximum amount of memory for the Java heap, let's say 200 megabyte. And then what this means is that there is more pressure now on the garbage collector, because first of all, JVM is lazy, and that lazy behavior is good, because you initially, when you launch your Java application, you tell JVM, hey, start with this initial amount of memory. You are allowed to request this amount of memory with operating system. Usually, I think it's around 100 megabyte or so, right? That's the default value, I believe. And then what happens is that JVM starts running your application. You allocate new objects, right? But as long as you don't get close to that initial amount of Java heap memory that JVM has requested from the operating system, and obviously in order to successfully launch the Java application, the operating system has to grant that initial request that the JVM does. And so JVM knows that, let's say 100 megabyte is initially available, but your application is run and you're only creating a couple of objects, and each object, let's say, has two integers, so two 32-bit or 8-byte, 16-byte. Even if you create 100 of them, you never pass like 2 kilobyte of memory. So there is no point to run garbage collector, even if you start creating garbage in the memory, because if your application terminates and then you've only occupied 2 kilobyte of memory, there was no point to run the garbage collector. And then after your JVM terminates, right before terminating the process, JVM returns back all the memory that it requested initially to the operating system, right? When you terminate your Java application, all the memory is returned back to the operating system. And that's true for any process, even something that is not based on the JVM. So in general, when you, in your operating system, when you terminate a process, the memory is returned back to the operating system. Now let's have a basically look at so I'm going to go back to the OOP, and here I'm creating a class for the new operator. We just want to explicitly look at a few of these concepts. Now the concept one was that so garbage collector does not necessarily run does not always run, right? Sometimes there is no point. Basically, sometimes there is no point in running garbage collector. So to clean up some of those objects that have been created and initialized in the Java heap, just because it depends, obviously, the main factor is the lifetime. So it depends on the lifetime of your application, and how much is the initial memory that JVM requests from operating system for the Java heap. Okay. So first of all, let's look at the memory. So let's look at the memory first. Let's look at the memory first. So there is this class called system class that provides some methods, functionalities that you can use to investigate how much memory is allocated at runtime. So when you launch your JVM, you can investigate what's going on based on for the internals of memory. Remember, memory is always one of the, or at least even today's, that RAM memory is very cheap and you can easily go buy 1 terabyte of RAM. Still, memory is considered the most precious resource that your application requires. That's why obviously it's not as important as what we had to deal with 10 years ago or so, but memory is still considered the most precious resource that your application has or needs, because every data is going to be loaded in the RAM, in the memory, right? And eventually at some point during the application, you as the end user or you as the developer of your application decide to dump some of the state or some of the data that is in the RAM into the hard disk as a permanent record, which is called persistence. Persistence of data means your application, all its data is in RAM, is a random access memory. So but then at some point you want to translate or transfer some of that volatile data into a more persistent way of storage, which is a hard disk, right? SSD or hard disk. These are persistent memories. whereas RAM is considered a volatile memory. As soon as you close the application, terminate it, all those data are gone, memory is returned back to the operating system, and operating system decides how to allocate it to other processes. So memory in JVM. So there is the system class. We use the system class. And then there is also another particular class called Runtime, which is dealing with the with this kind of runtime stuff. So let's start with the runtime class. Runtime class, with this comes in the form of singleton design, which means whenever you launch your Java application, there is only one instance or object of this class is allowed. So I'm going to open this runtime with basically JDK 16. And there are some very interesting methods. First of all, you have a public static method that returns the instance that is the current runtime, right? The constructor is private, so for a singleton, you can never call the constructor. So use this static method to get the only. You have the exit, just like the you can exit your JVM with a flag, and these days we don't really care about this flag, but in the earlier days, obviously, whenever a process terminates in the operating system, a process can return a exit flag or exit signal to the operating system. And the convention is that exit flag 0 means that the process terminated correctly, right, with no problem. If there is some exit flag like exit -10 or -1, some negative number, then it means the process terminated with some error or something, right? So if some error happens, the process terminates, but then the return flag is not 0. So conventionally 0 is returned for a normal, correctly or normal process, normal termination, which means the operating system knows, hey, everything went well. So add shutdown hook, remove shutdown hook. These are more advanced topic. Halt, maybe you want to halt the JVM. Exec, if you want to execute a command directly. And not surprisingly, these return some construct that emulate a process of the operating system. Available processor. So that's one thing that you can ask. So let's get the runtime. Var runtime is runtime get runtime. This is again returns the current runtime, and then we can say sysout runtime dot available processors. I want to see how many processors are available on my computer so that the JVM can take advantage of them. And it tells me 8 processors. Obviously, my hardware has 4 processors, 4 physical cores, and then hyper-threading kind of emulates 4 extra cores. So 8 extra cores, that's the logical processors that the operating system sees, right? So this is the logical number of processors, not the physical cores. Logical number of processors, not the physical cores. Again, if you're not familiar with this kind of concept, that's fine. These are more like computer science stuff. But the idea here is that the number of processors that your operating system sees could be more than what the actual physical number of cores is. That's because advanced CPUs, like the Intel ones, they support hyper-threading, this kind of stuff. So they have more capabilities in terms of processing. So that's one method. The other one, free memory, total memory, max memory, and the garbage collector. And these are all native methods, right? And because runtime is a final class, it's not final, but it's still public, but it's a singleton. Whenever you have a singleton class, or basically a class that has private constructor, you can never inherit from it. So you can never change the behavior of this runtime class, which makes sense because this deals with the internals of the JVM. If somebody could inherit and override this method, for example, free memory, then things can easily go wrong, right? So so these are native. If you are not familiar with the native, it just means native uses the implementation for this method is inside a C++ dynamic library, which you probably know where that is. So if I can quickly show you. So if you go to folder, and then we say that basically library, and then Java virtual machines, and let's say we're using JDK 16. So in the it depends on how your JVM has been packaged for your operating system. In macOS, there is a macOS, and in the macOS, this is the JLI, Java Library Interface .dynamic. This is dynamic library. This is a compiled C++ code, and this is basically where those operating system specific part of code is that these native methods are implemented. So in the more advanced lectures, I will show you the actual C++ source code of the JVM, and we will go through all the details of how these methods have been implemented in C++. But for now, these are native methods. So the Java doesn't provide, the Java source code doesn't provide implementation. JVM just reaches out to a dynamic library that has the compiled code from a C++ implementation and just calls them. So we can check, so sysout, so let's see, sysout runtime free memory. We want to see how much free memory we have, and you can run this during your application. So right now I am calling it right when the application starts. And it tells me that we have this, and this comes, I believe, in bytes. So if we say sysout runtime free memory, or maybe let's define a new variable here. So so this returns, I believe it returns a long, because the memory could easily go. Remember, an integer is 32-bit, int is 32-bit, so it can eventually show us up to 40 gigabyte, right? And because this I believe it's more like 3 something gigabytes, so definitely it doesn't show more than 4 gigabyte. And we know that these days we can easily have a computer that has 16 32-bit gigabyte of RAM. So therefore you can launch your JVM with 10 gigabyte of memory. That's very easily achievable these days. It's very cheap and easy to do that. So that's why these return long. Long is 64-bit, so it can easily give you an accurate number of bytes up to a couple of terabytes or zettabytes, right? So we want to use long 64-bit for bytes to represent bytes of memory. So we're going to say long memory in bytes is runtime free memory, and then free memory in bytes equals basically plus memory bytes. And then let's copy this again, and we want to go kilobytes. And kilobytes, usually the capital B is a short notation for byte. Every byte is 8 bits, right? So, and then long memory in kilobyte is memory in bytes divided by 1024. And then long memory in megabyte is memory in kilobytes, KB, divided by 1024. So every power of 10 for base 2 is 1K. If we were using base 10, then it's 10 to the power of 2, 10 to the power of 3, right? So long memory in gigabyte is memory in megabyte divided by 1024. So let's see. So KB, and then memory in KB, and then memory is MB, and memory in GB, gigabyte, MB and GB. So if we run this, we have okay, kilobyte, megabyte, and gigabyte. So 257 megabyte. And because we're not really allocating any memory, obviously when you launch your JVM, some memory is allocated to this variable. This is like a pointer, 32-bit. Some memory is allocated for this array. We're not passing any command line arguments to our Java application, so this just holds a pointer reference, 32-bit, and these one are 64 bits or 16 bytes. So really we're not consuming any megabyte or kilobyte size. So this is just really the initial memory that the JVM launches with, right? And So this is another thing. So you can get some information at runtime about how much memory is available, free memory. There is another, obviously there are two other methods, total memory and max memory, right? So free memory is how much is currently available and free, I can use it. So let's create a new method, public static void print free memory, right? And let's move all these into this. And remember, there is even if we have multiple methods that call this get runtime, this runtime is always a unique instance, is the same. That's because this is how the singleton is implemented. And so free memory, now we want to also have a method that prints total memory. And then let's say total memory. Probably we don't need to have this. Let's move this these two lines of code for the processors in the main. So we still have this in the main to print the number of processors, and then let's remove that line from here. We still need the runtime, and then yeah, we still need the runtime. So instead of free memory, we say total memory. And then I'm going to have one more method. Remember, we have free memory, total memory, max memory. Max memory is that, first of all, if you cannot pass the max memory, that's the maximum that the JVM knows that it can request from operating. After that, then there is more pressure on the garbage collector to run, more frequently run and free more memory, so that memory becomes available for your Java application. So max memory. Instead of total memory, we say max memory. Instead of total, we say max. And I'm going to do a sysout with some, let's say, stars to separate these printouts. Let's put them before and after. And one thing to keep in mind is that these are not necessarily very accurate. So if you call this method and it tells you 257 megabyte, in reality, it could be something more or less. But I mean, there could be maybe 1%, 5%, or even 10% error. That's fine. But these give you a ballpark of what's going on. So these are not supposed to be extremely accurate. Just have in mind. So if we run our application, let's say print, we're going to start with total memory, max memory. So print max memory, print total memory, and then print available or print free memory. So let's run this and let's look at the results. So we have 8 processors. Max memory is 4 gigabyte, right? Max memory in gigabyte is 4. This is how the JVM is currently configured. It can only request up to 60 basically 4 gigabyte. And the reason is that, if you recall in my description in the past lecture that we had, we said that by default JVM uses compressed OOPS, which means it uses 32-bit pointer types for objects that you create, 32-bit references or pointer types, right? References are behind the scenes, they're pointers, and a pointer on a 64-bit machine has to be 64-bit. But JVM is aware that with the 32-bit pointers, you can address up to 4 gigabyte of memory. You cannot go beyond that. And if your application doesn't require more than 4 gigabyte of memory, then by default JVM starts with this compressed OOPS idea, right? And so that's the default thing. And then total memory in kilobyte 260. So this total memory 260 is what actually JVM requests from the operating system by default when you launch your Java application. So when you launch your Java application from the command line or from your IDE, then JVM asks operating system, hey, give me 260 megabyte of memory. And obviously, if the operating system is low on memory, it would not grant that request, and your JVM crashes with some out of memory error or memory unavailable, something like that. All right. But then after the total memory is 260, we see that the free memory is 257. So we only use like 3 megabyte. And the obvious question is, we didn't really allocate any object. Why is it that we got 260 megabyte from the operating system and immediately 3 megabytes is gone? That's just because a lot of stuff behind the scenes happens in JVM. So JVM always needs a little bit more memory than you actually see or in Java code, just because JVM does some bookkeeping, some it writes down the stack frame of the methods or like some other stuff behind the scenes. So you always end up with you always lose some memory because of those things, right? That's the price you pay in terms of more easy development, because a lot of the stuff are behind the scenes inside the JVM. So I hope you enjoyed this lecture. In the next lecture, what we're going to do, we're going to use the new operator and allocate objects and then monitor the total memory, the free memory, etc. And to see how this free memory decreases over time until the garbage collector is run, right? And right now, it's, you see, I launched my application, I did some stuff, my application terminated, but I never used the garbage collector, right? I could actually do this. So if after the print total memory, I manually call the GC, this just gives a request to the JVM that, hey, it's kind of like a good idea. So this is a hint to JVM, hint or request that maybe it's a good idea to run a GC here. It's just a maybe. We're just saying, hey, JVM, maybe it's a good idea. But then it's at the JVM's discretion. Maybe JVM decides, yeah, probably it is, or maybe not, because there's lots of memory available. But let's see what happens. You see what something very interesting happens. We started with 260 memory when we launched our JVM, but after the GC was run, we have 17 megabyte. That's because they actually did something very cool, I believe from JDK 16, that if you launch your application and explicitly request a GC, the JVM has this right to monitor your application, and if JVM decides that you really don't need this amount of memory, JVM actually returns part of that memory to the operating system. So after this line of code, basically the memory available for your application has gone down because JVM decided, hey, up to this line you didn't do anything interesting, so you probably don't need that amount of memory. Now let's print the total memory right after that to see what happens. So we started from 260 megabyte. After we asked the JVM to see if it's a good idea to run GC, and JVM agreed and ran a GC, our application now only has 20 megabyte. So we lost 220 megabyte just because the JVM realized that up to this point, application didn't do anything interesting. So it probably doesn't need that amount of memory, right? That's the speculation that JVM did. So it reduced the amount of memory from 260 to 20 and returned 240 megabyte back to the operating system. Now, obviously, if after we do this and the JVM does this reduction, if the application suddenly starts to allocate lots of memory, then JVM has to go back to the operating system and kind of ask to get that memory back, because JVM realizes that you need this. So I think this kind of memory reduction was implemented from JDK 16. You can just Google it to see which JDK this was actually implemented. Now I can, for example, change my runtime. Let's say to let's have a let's see if I can quick switch, for example, to Java 8. Now if I switch to Java 8, I'm going to get a compilation error because first of all, Java 8 doesn't support this var, so if I run this, let's see what happens. We probably get compiled. Okay, so it's compiling again all the class files, and we're going to get a compilation error just because var is not supported. So let's start with JDK 15. Let's see if we change our runtime to JDK 15. The Eclipse has to recompile all the classes in this project, but let's see if we can run this. Wait for the so project clean. Let's clean our project and see if Eclipse recompiles or not. Let's see if it still has problem. All right, so I'm going to stop this lecture. In the next lecture, I will show you what happens if you switch to, for example, Java 15 or Java 8, and we will see if this behavior of memory reduction also happens in the other versions of the JDK. I hope you really enjoyed this lecture. Please stay tuned, and I'll see you in the next one.